Alright, what's up guys? In this video we're going to pick up with some differential equations and we're going to solve a Bernoulli's ODE again. So as to solve the Bernoulli's ODE, we've got y squared y prime minus 5y cubed is equal to e to the negative 2x. And it's basically an initial value problem because we're given an initial condition y of 0 is equal to positive 2. So it's been a while since we've solved the Bernoulli's ODE. So I thought, why not do another one? So remember, the form for this type of linear equation is going to be y prime plus p of xy is equal to q of x multiplied by y raised to the n. So that form may look familiar because it looks very similar to a linear first order differential equation, which is exactly what we're going to do. We're going to do a substitution, and then we're going to convert it into a linear first order differential equation, which we'll solve using integrating factors. Come back, do the substitutions, or put the substitutions back in, and solve for y of x basically. So I've done these before, so if you don't know how to solve Bernoulli's equation, I do have other videos on it. So remember, the substitutions that we do are v is equal to y raised to the 1 minus n. When we differentiate that, we get v prime is equal to 1 minus n multiplied by y raised to the negative n multiplied by y prime. Or if you like me and you like positive exponents, you can write it as y prime is equal to 1 minus n multiplied by y prime divided by y raised to the positive n. So as you can see here, the differential equation is not in the correct form. We got y squared in front here, so we need to divide both sides by y squared. And sometimes it won't come in the correct form, so don't expect that all the time because it won't happen all the time. So sometimes you'll need to get it in the correct form. Professors are good for finding problems that aren't in the correct form, and they oftentimes will put a little bit of work on you so you can get it in the correct form. So you're going to divide both sides by y squared. So that means you divide everything by y squared. So what that's going to leave us with is y prime minus 5y is equal to, I'm going to bring this y to the negative second up top. That's going to make it, y to the second up top, make it y to the negative second. So this would be e to the negative 2x multiplied by y to the negative second. We need to get it in that form anyway because we need our y raised to the n. So let's identify what the p of x is. So the p of x here is negative 5. Q of x is e to the negative 2x. And then n here is negative 2. So now we need to do the substitutions. V is equal to y raised to the 1 minus n. So that's going to be v is equal to y raised to the 1 minus negative 2, which is basically 1 plus 2, which is 3. So v here is y cubed, which means that v prime is 3y squared multiplied by y prime. Now you plug your substitutions into the differential equation, so we'll get 1/3 v prime minus 5v is equal to e to the negative 2x. But of course this is not in the correct form. We need to multiply both sides by 3 because we need to isolate v prime over here. We can't have a 1/3 in front of it. So let's just multiply both sides by positive 3. And if we do that, we'll get v prime minus 15v is equal to 3e to the negative 2x. So hopefully that makes sense. Now this is a linear first order differential equation which you can solve using integrating factors. And we got it in the correct form already. So recall that the integrating factor that's going to be e raised to the integral of p of x dx, or p of t dt, depending on what the independent variable is. And the integrating factor is given by mu of x is equal to, or mu of t, depending on what the independent variable is. But mu of x here is, again, e raised to the integral of p of x dx. So that means that our integrating factor here is e to the negative 15x. So what we do now is multiply both sides of the equation by the integrating factor. So we'll have v prime, and I'll put it in parentheses to make it a little easier to follow, e to the negative 15x minus 15v e to the negative 15x is equal to 3e to the negative 2x multiplied by e to the negative 15x. Okay. Alright, so we'll need to simplify on the left hand side and apply the product rule. And so if we do that, we'll end up with e to the negative 15x v prime is equal to 3e to the negative 17x. Now we need to integrate both sides. So we're going to integrate e to the negative 15x multiplied by v prime is equal to the integral of this side, 3e to the negative 17x with respect to x. The integral here just undoes that derivative, so we'll just get e to the negative 15x multiplied by v. Then we integrate this side. So recall that the antiderivative of e to the negative 17x dx is negative 1 over 17 e to the negative 17x. We have to multiply by the constant 3. So we'll get negative 3 over 17 e to the negative 17x plus c. Now we need to isolate the v. So divide both sides by e to the negative 15x. And we'll get v is going to be equal to negative 3 over 17 e to the negative 2x plus c e to the positive 15x, because I'm going to move it up top to make it positive, or vice versa. You could write it v is equal to c e to the positive 15x minus 3 over 17 e to the negative 2x. Okay. All right. So now we got to do go back to our original substitutions. If you remember from earlier, where did I put it at? No, right here. Remember that v was equal to y cubed, so we got to plug that back in. And then we can apply the initial condition. So we get y cubed is equal to ce to the positive 15x minus 3 over 17e to the negative 2x. Okay. So now we apply the initial condition. So recall that our initial condition, which I'll just denote IC here, was y of 0 is equal to 2. So we stick in a 2 for y and a 0 for x. Recall that 2 cubed is 8. Okay. So essentially, and if we e to the 0 is 1. So if we stick in a 2, we'll get 8. is equal to C minus 3 over 17. And we simplify that by adding by adding 3 over 17 to both sides to solve for C. So we get C is equal to, what was it? C here is going to be 139 over 17. Okay. And that's really all the initial condition is. It's just allowing us to solve the constant. Now you just got to plug it back in there. So you got we got y cubed is going to be equal to 139 over 17 e to the positive 15x minus 3 over 17 e to the negative 2x. Now we need to solve for y, or y of x in this case. So you can either take the cube root of both sides, or you can raise both sides to the 1/3 power. That's the same thing as taking the cube root of it. So we'll raise this side here. I should have made this a little bigger. We'll raise that to the 1/3. And we'll raise this to the 1/3 as well. So obviously the 3's go away. So this would be y of x is equal to 139 e to the positive 15x minus 3e to the negative 2x. And since we have a common denominator of 17, I can just put the 17 down here. And again, I don't know, come on, pen. That's going to be raised to the 1/3. So if you took the cube root of both sides, that would have been perfectly fine as well. Or if you want to do it the other way, if we taken the cube root, the same thing as raising it to the 1/3. So if you took the cube root, that would have been fine if you wrote it that way, but maybe a little better to write it this way. So your final answer for this differential equation, when we actually solve it here, Bernoulli's equation, is going to be y of x is equal to 139 e to the positive 15x minus 3e to the negative 2x, all divided by 17 raised to the 1/3. And that's your solution. Okay. So I hope that made sense. Just another quick example of Bernoulli's equation. Pretty straightforward process. But you will need to be familiar with linear first order differential equations and how to solve those using integrating factor. Alright, so that's going to be it. So I'll see you guys next time. Let me know if you got any questions. Y'all take care.